Good morning. So, we'll continue with the topic oxidation in heterocyclic chemistry, and as you know, this is a very vast topic, and in the last class we summarized some of the important oxidizing agents and their uses in heterocyclic chemistry, and we will continue with the same topic because a range of oxidizing agents used in heterocyclic chemistry is a very big one, and today we talk about few task specific oxidizing agents. What does it mean? It means some of these oxidizing are only meant for a particular kind of oxidation, okay, and which include oxygen, hydrogen peroxide based oxidizing agents, brominating agents like bromine and NBS, and then manganese dioxide, ruthenium dioxide or ruthenium tetroxide, then IBX, all of us know what IBX is, and then we will also talk about oxyridine, and then little bit of Tempo, tetramethyl piperidine oxides. Okay. So, this is in nutshell the list of the oxidizing agent we will cover today, and but to begin with, of course, we will continue with the example we gave you last time. This is a I think we have here, you can see for fural in the presence of singlet oxygen, and singlet oxygen is as I said before routinely produced by passing oxygen through a solution of eosine or rose bengal at room temperature is perfectly all right, even at 0 degree centigrade. But what is the product? How do I know? One can see that there is in the starting material you have an oxygen that is belonging to furan and an oxygen belonging to aldehyde. So, when I say task specific, means there are three different kinds of tasks often the oxidizing agents do in heterocyclic chemistry. One towards the ring, other towards the particular heteroatom, and third of course the functional groups or the vicinity of the functional groups. So, these are the three different gross classifications of oxidizing agents, effect of oxidizing agents, rather action of oxidizing agents. Okay. And so, what do you think now in this case? So, that means there are three possibilities: it can attack the heteroatom, it can attack the vicinity of the heteroatom, and it attacks the it can oxidize the ring itself. Okay. And so, now we know there are two kinds of oxygens, singlet oxygen, triplet oxygens. Grossly speaking, triplet oxygens behaves like a radical, and singlet oxygen does not behave like a radical. Many of you know, simply because in a reaction to the triplet oxygen, if you add inhibitors, radical inhibitors, the reaction is inhibited, but in case of singlet oxygen it is not. And typically, there are two kinds of reactions of the singlet oxygens. What are the two kinds? I think I told you last class. Singlet oxygens, Diels-Alder and in reaction. Fine, perfectly all right. Okay. And to begin with, also you have to remember, because you will be teacher in one day or 2 days. How is hydrogen peroxide produced industrially? To okay.
With hydrogen peroxide and reverses with hydrogen.
No, just you missed a very important point. See, conversion of oxygen to hydrogen peroxide means is an equivalent to reduction. So,
it is done by hydrogen and catalyst.
No. Okay. Very quickly, that is an example of Diels-Alder reactions of singlet oxygen. You are very right. I think this I taught of course in the last year also. So, this is this. Then you have to have a reducing agent. Normally it is a sodium bisulfite or sodium dithionite. Sodium dithionite means Na2H2O4. Okay. And then you pass oxygen, actually it gets converted to during this process it gets converted to this anthradiol, right, and then it goes to corresponding the Diels-Solder product. So, Diels-Solder product means so this is the way actually this that means the basic commercial hydrogen peroxide is produced these days. At a time when we studied, that was barium peroxide, okay, paste. But now then, of course, then all of us know this is hemi-acetal form, hemi-acetal forms, and it undergoes cleavages to give hydrogen peroxide as the final product, and then the quinol goes back to the quinone, and then it undergoes recycling. So, it is a typical of Diels-Solder reactions. So, in this case also, in this case what we can expect? We can expect a Diels-Solder reaction of the singlet oxygen of singlet oxygen. So, what next?
Sir, how they produce singlet oxygen in that reaction medium, that is commercial production of hydrogen peroxide?
I think this is beyond the syllabus though, but I can tell you the answer. In the last class you have not, I do not know whether you have attended or not, there was an oxidation called Cron oxidation. It oxidizes the benzylic oxygen because of the internal, the anthraquinone itself is a nice photosensitizer. Okay. So, so in this case also it will be doing like this. What next? So, what is the next possible thing? Hydrogen abstraction. Hydrogen abstraction is a possibility. Then you get this. Okay. So, if hydrogen oxidation is a possibility, then one can expect that this can undergo further oxidation to the corresponding carboxylic acid. Okay. And then you have a carboxylic acid, you have so many of heteroatoms. So, there is a possibility that it can decompose to so what you will have now, oxygen here, oxygen minus, and then you have here double bond. That is it. What is it? It is nothing but of course during workup. So, what you will get? You will get this one, and if that means starting from a heterocycle, you are getting a new heterocycle, and mind it, it is equivalent to a cis aldehyde and a cis carboxylic acid. And if you try to make these, otherwise I will find it is a very tough job. First of all, you have to have a selective oxidation done, and that thing. So, there is another way of doing it. I mean, there is another way of doing it. Just give you information. This is an example. Again, if you run, and you have a group R, and in this case, the singlet oxygen is produced separately. T, P, and then light. TPP is basically what is it? Louder. No, in this case, so it, not really. Not see, we are talking in context of singlet oxygen. So, it has to be a photosensitizer. The photosensitizer. Well, I will give you the product. The product is again a cis derivative, cis compound. Cis compound, you will have this product here R, and what you can see now the ester is protected. So, what you will have, I mean this peroxide also sometimes undergoes decompositions, and this, the thermal conditions undergoes self decomposition to corresponding the oxo compounds, and it is nothing but the ring cleaved product, and of course, if you have HCl and chloroform, then you can go to the corresponding the trans isomer. These they call esters here, and this carbonyl, and these are. That means, you can get both the isomers and nicely with a stereo defined way, but TPP stands for tetraphenyl porphyrin. All of us know that is the classical photosensitizer, tetraphenyl porphyrin. So, tetraphenyl porphyrin, right, porphyrin. Okay. Let us look at one more example of this on this use of singlet oxygen. This has been used in the total synthesis of a very complex molecule, and that begins with a bipyrrolic compound. That means pyrrole here, and then one more pyrrole unit, and N-methyl. And as I think often I write, okay, in any case I will write here in this case as a diester, 2,5-diester here of the pyrrole, and then you have also 2,5-diester on the other ring, and then you have a methoxy group up here and a methoxy group up here. Little chemistry, and then we talk about the heterocyclic part. So, this is a very not really, it is a dipyrrolic molecule, and there are molecules which are natural products and also contains these 2 pyrrole units. Now, we perform a sequence of reaction. First is lithium hydroxide, and then trifluoroacetic acid, and the third one is diazomethane. So, and what do we expect? This is basically the preparation of the starting material. And so, first is lithium hydroxide, all of us know it is a popular now reagent for ester hydrolysis. Classically sodium hydroxide, potassium hydroxide used to be used, but now in research laboratory most people use lithium hydroxide. I think all of us know the yield is very high, it is soluble and it can be controlled. So, in this case the lithium hydroxide can be used for control hydrolysis only for 2 ester groups, control hydrolysis for 2 ester groups. There are total of 4 of them, right, and so you can now, since we know a bit of chemistry, so we can predict, right. So, what will happen? Pyrrole units remains intact, methoxy as all of us know would remain intact, and this again the methoxy the impact. Now, 2 of the ester groups would be hydrolyzed. Which 2 ester groups would be hydrolyzed? Any guess? See the effect of methoxy. Many of you know this methoxy, the one adjacent to the methoxy would not be hydrolyzed because of the lone pair of the oxygen. It would reduce the nucleophilicity, electrophilicity of the ester group. So, that means the other one would be hydrolyzed here. So, in this case that means you will have 2 ester groups and the carboxylic acid. Oh, okay. Right. Then I am caught. Okay. Then I have to see that. Then okay. Yes. Trifluoroacetic. That means apparently all of these ester groups have been hydrolyzed. Okay. But there are methods. But you can use for controlled hydrolysis. So lithium hydroxide is very useful. Even I have done it in my research career. If you have a diester. With controlled amount of sodium hydroxide, you can do it half esters. That is a standard. Okay. Then maybe we will clarify after looking at the literature. Sometimes what happens, is a little bit of the byproduct is formed, that is converted to the corresponding diesters. That is also possible. So, but I assume that it is mainly these 2 esters are preferentially hydrolyzed. Okay. Now, what next? Actually, this is the most critical example of photo-oxidation. Again oxygen, and then this catalyst, that is rose bengal, the popular catalyst, and then light, and something else is required, something, because what you will see is collidine, and collidine is, what is collidine? Collidine is a pyridine base. So, you have to know now, it is in heterocyclic chemistry class. That means, a lot of heterocycles are used as reagents in organic chemistry. Collidine is a methyl substituted pyridines. Okay. Then what is the product? So, you have so many functional groups, nitrogen, etc., etc. There are 3 different kinds of modes of oxidation: ring, substituent, functional groups, etc., and these vicinity of different heteroatoms. So, in this case, the answers obviously would be related to this photo-oxidation of the ring, and so what you will find, it will form again a Diels-Alder thing, Diels-Alder intermediate with oxygen, singlet oxygen. Then you have carboxylic acid, and then the ester up here, and the double bond. So, similarly, the other ring also would be double bond, and then it is oxygen again, oxygen, then this N-methyl group, and then what else? One side you will have this carboxylic acid, and other side you will have the ester groups. So, basically you can just repeat, just sit down, just write only one side, that is enough. You do not have to repeat both the sides. Then what next? What next? So, that up to this point it is perfectly all right. So, fragmentation, and what is the driving force for the fragmentation? No, part of it, right. So, carboxylic acid, yes, you have a labile oxygen, etc., but the driving force of this reaction, actually this does not stop here, it further undergoes fragmentation reaction. So, fragmentation would take place like the previous one, that is it. So, what you will see, I think I will just only write this part. Okay. This part would be the ester part, this is oxygen minus, which will eventually would become OH, and then what else? In this case you have oxygen here, and this is methyl group, and then you repeat the other thing. I do not want to write this. So, basically fragmentation would be taking place, and this is the structure of a natural product called chrysoharmidine. So, that means this is very, what it means is basically useful synthetic transformations, which can also give rise to natural products of complex nature. Okay. So, all this is all about this singlet oxygen, but I have not got the answer yet. What is the driving force for these fragmentation? I am still looking for, I am waiting for the answer. Whenever you write a reaction towards the forward directions, you have to keep it in mind. See, now we are at advanced level, we have to know the reaction mechanism. Or the reaction mechanism initial stage in BSc or first year is basically the electron bookkeeping. When you go up little bit, then you have to explain in terms of the transition state, and crudely speaking or grossly speaking, you should speak in terms of driving forces. What are the driving forces? Why the reaction is not stopping, it is further progressing towards the right direction. What is that? That is one of it, I said before. One more important point. Why should this reaction Right. So, that means we that means bond strength, weak bond strength of the peroxide linkage. Okay. And now let us talk about one more reaction with just regular oxygen. So, I give you the reaction first and then we will tell you what it is and what is the product. It is a carbazole derivative. It is a carbazole derivative with of course, means indole moiety here the air ring nitrogen. So, you can say it is actually a carboline derivative. So, carbazole is 2 benzene ring, but when you have one of them is pyridine, there is known as carboline derivative. So, it is a quite famous nucleus. Now, the simplest oxidation often we do also in our lab for anthraquinone chemistry, and just air, sodium hydroxide and DMF, and you do not have to heat anything and just room temperature, and PG stands for often we write protecting group, and protecting groups are normally amides like BOC, all of us know BOC, butyl oxycarbonyl, acetate, benzoate, and then CBZ I think benzyl oxycarbonyl, CBZ and toside, all of them actually belong to the amide groups, and this is and most of the cases nitrogen protecting groups are amide protected groups. Okay. So, what do you expect out of this reaction? It is a very simple reaction though, no complication, just oxygen, plain oxygen, and there is no photosensitizer. So, it is a base catalyzed reaction, and apparently it proceeds through the triplet oxygen oxidation, and the product I will give you, the product is now it is a rearranged product. And that is it. What is it? It is a quinoline derivative. It is not really a quinoline derivative, it is a little something different, but in any case what you see here, the middle ring got expanded and the right terminal ring got contracted. So, this is and if you overall look at it is an oxidation reaction because oxygen is incorporated. So, this side of reaction is pretty well known in heterocyclic chemistry, and this is known as Winterfell oxidation. So, and what is the pre-requirement? The pre-requirement is essentially the NH. If you have NH, NH would form a negative charge here, and then eventually after delocalization etc., it will capture an oxygen up here and it is a 4 member. That means, it is a formally kind of a 2+2 cycloaddition kind of reactions, 2+2 it is formally, but it goes by the anion formations, nitrogen anion formations. This anion forms this oxygen attacks here, this anion goes to this, and then this oxygen minus this come back, and then you can write an intermediate of this kind of dioxy. So, dioxygen you can say or oxide, okay. And then what? And then all of us know when the 2+2 cycloaddition takes place, the next normal reaction is again a 2+2, again in this case the driving force is the weak peroxide linkage. So, it would form I mean this, then oxygen up here, that is it. So, what next? You can guess now. Just intramolecular aldol type of reactions. So, since we know the product, we know it forms the carbon ion up here, it would undergo aldol type of product, you get this. So, this is also quite prevalent in heterocyclic chemistry, this Winterfell oxidations. That means, in summary, oxygen is a very good useful oxidizing agent. Let me go to the another kind of reagent, which is a basically reagent called I think all of us know, the bromine. Bromine in heterocyclic chemistry also is very good oxidizing agent. For example, if you start with a furan compound and you use excess bromine. So, what do you expect? Excess bromine, acid, yes, I would assume acid probably, and what else? Okay, I'll give you a hint. Let us say this is taught in BSc. If you take furan and add bromine and in just one equivalent of bromine and methanol, what you will find? Louder, right? Because the intermediate, the intermediate dibromo compounds are pretty reactive by virtue of the having lone pair on oxygen, and all of us know oxonium ion is more stable because of the lone pair effect, and so that means this like mom chloride. All of us know mom chloride, they are pretty reactive because of the oxygen lone pair, it produces stabilizes the adjacent carbocation. So, on the similar ground this this sort of intermediate would be pretty reactive, and so the product would be, all of us know, the bromine would be substituted by methoxy on the both the sides and we get this product. So, one can say one can view this reaction as an oxidation reaction. If you look at the number of oxidation level or these or else you can say it is a dearomatization process. So, oxidative dearomatizations. Okay. And in this case also you would expect a very similar reaction, but since equivalent of bromine is quite high. So, one would assume this nuclear bromination also, nuclear bromination will take place. That means, what I can say CHO here and this, let us say the nuclear bromination also can take place, right. Nuclear bromination can take place, and when I say bromine, 5 molecules bromine means of course the water is there and this bromine. Anything else you can expect? Eventually you just sit down and do this work and you will find it will give a nice compound, again a cis derivative. So, you will hydrolyze and then ring close and eventually you get this sort of aldehyde carboxylic acid. Now, if you just change the substrate, say initially it was furan, the next example was furan carboxyaldehyde. Now, we have a substrate, let us say just a little change. So, it is now hydroxyfuran and then reagent also is changed little bit, NBS and water. What is it equivalent to? Bromohydrin, bromonium ion and OH. If you do this, it is a nice again sort of a bromine addition kind of things, ring opening and ring closing, and this reaction has been termed as now acmatoic reactions, acmatoic reactions. This is under the name of a Polish scientist, acmatoic reactions. What is it? It is a very useful reaction though, again an oxidative dearomatization kind of reactions. The product that is formed is double bond, and then you have this hemiacetal kind, and then oxygen here and this methyl group. How do you view it? Okay, mechanistically one can see this since it is a bromohydrin, you can write that okay, this bromination takes place, this hydration takes place, whichever we like. Then you have OH group up here, and then just it opens up and so what you will see, this is double bond here, and then this should be equivalent to aldehyde, right? This should be equivalent to aldehyde, and then this should be equivalent to a ketone, and now you have this OH, and this is the methyl group. Right? And what next? I think all of us know the ring closing. Ring closing takes place. This is a very useful reaction, and this particular reaction, why it is now named as Akhmatov reactions. I mean, if you look at the mechanism, it is a very simple one: addition, ring opening, and ring closing. Chemistry wise, it is not a great one, but it has been used on several occasions, especially the substrate. The pyranone is very useful in many synthetic transformations. And let me give you a quick example. Like maybe you will be able to tell me the answer. I think I will skip some of the examples. Let us look at one more, a very similar kind of oxidative dearomatization. Here is a furan, then you have a side chain with TBS, tertiary butyl silyl, and on the other side what you will have, you have again a side chain, mind it, you have now OH group up here. So, it is not a furan carboxylate, it is a furanyl alcohol. Okay. Well, and then the reagent here, you see here the reagent, again we are talking about this peroxo compounds now. This is a separate one now. So, initially we talked about singlet oxygen, triplet oxygen, then brominating agent, bromine and NBS. Now, we are moving towards the peroxy reagents. So, tertiary butyl hydroperoxide is basically a peroxy reagent based on hydrogen peroxide, but is soluble in organic solvents. Okay. Now, what happens if you react this with and then vanadium oxo acetyl acetonate. Okay, that is catalyst, and the room this is 0 degree centigrade. Does it remind you anything about the reaction? This combination of reagent? Moon. I thought you memorized the whole book of Carothers. Anybody has memorized Carothers book? Epoxidation, yes, surface epoxidation reaction. So, what do you expect out of it? But in this case, it is a furan case. Surface epoxidation, if you recall, it requires the presence of a hydroxy group. Surface epoxidation requires the presence of a hydroxy group, because that hydroxy actually coordinates the titanium. Okay, in this case, it is vanadium. So, and this is not an asymmetric version, it is a non-chiral version. Now, what is the product? I think you should be able to write the product, right? Again, what I said is a dearomatization product, and let us should we work it out? Okay, maybe. So, what do you do? We begin with this. I think we will just write R on this side and R on this side, or we'll take this OH group because it would be participating in the reactions. Let us say R prime. What next? Epoxidation. Let us say we do this epoxidation. That's it. There are two double bonds. I have done the epoxidation on the side of the hydroxy. Okay, nobody knows, what happens, but it is likely that the reaction would be directed by the hydroxy towards this double bond neighboring to it, and then you have a double bond here. What next? What next? maybe simple hydrolysis, let us say just simple hydrolysis, that means water addition take place. This is OH and this is R prime and this is R, and this is simply a water addition, let us say, and in the during the reaction, okay. And so it again it opens up and this. So what you will see, then you will have the ketone on this side, R side, this, then you will have a hydroxy, and then one more ketone, and then you have one more hydroxy, and then R prime, right. Okay. So what do you expect then? Next would be ketalization. So that means we will have now, that means 1, 2, 3, 4, 5, 6. So we can blindly write it is a pyran ring structure, right? Pyran ring structures. You have OH up here, this then R, and on this side we will have R prime, then next to this one is this, and this OH up here, right, and this OH this, and at some point it loses water. So what do you get? Is a pyranone. So you got a pyranone, and this is OH, and this is R, and this is of course then R prime. So net result, what is the net result? It is very similar to this. It is a new version of basically Akhmatowicz reaction. Only thing that the reagent is different. It is the surplus reagent. Okay, and this so this is nice. That means, and in this case it is a peroxide compound. Oxidizing agent is a peroxide, not the NBS. Okay. Now look at one more important reaction. This is selectivity. That means selective oxidations. When I say to begin with, this is task specific, means the reagents are sometimes very specific, and in this case very selective. Let us say I give you an example from my lab, where we made a few years ago a compound of this kind. So obviously it belongs to a heterocyclic compound. Now I treat this with a peroxide compound, hydrogen peroxide and acetic acid. I think all of us know what it is. It is a equivalent to paracetic acid. Now we have all kinds of possible oxidations. It is an oxidizing agent, all of us know. Then we have a thioester, we have a sulfur, again you have a neighboring alpha hydrogen, you have another sulfur. So which one do you expect? Okay, selective oxidation would be taking place. That means just one single oxidation took place, either at the ring or at the alpha position or at the heteroatoms, and then you have two heteroatoms, then one of the heteroatoms. Okay, the guideline is very simple. The one that is most electron deficient would not be reacting. So that means actually in this sulfur is very many of you have to remember at the end of this course, you have to remember of all heteroatoms, sulfur is most susceptible to undergo oxidations. Okay. Even nitrogen, of course, provided all other things are very similar structurally. All other things are similar. Sulfur is more prone to undergo oxidation, followed by nitrogen. Of course, oxygen itself is oxygen. So there is no question. That means when you talk about now, when it comes to the differentiation between the two different kinds of sulfur, the sulfur which is of course more nucleophilic in nature, and in this case, because of the adjacent carbonyl, the ring sulfur is not really very nucleophilic. So the oxidation takes place. The oxidation takes place at the other sulfur, and the yield is very good. So in fact we wanted a sulfone, and that's what we got. And let me give you one more example. This is a little complicated, but you don't have to write or memorize though. Just get the point here. This is a benzothiazole. Benzothiazole, then you have a sulfur up here, and then I may be wrong somewhere, maybe I have no idea. Oh no, double bond, sorry, this is not a double bond, this is not a double bond, sorry, single bond, this methyl group here, then you have I mean all kinds of groups here and there. This is TBS, and then you have a amide bond here, and then you have again a in this case TB DPS. Okay. So, by giving you all these, now does it tell you anything about this structure? Anybody can recall what is this structure famous for? Close. Is close. Is close. Actually, this is a reaction. This is a reaction. So you have been taught in the last year. This is a. So what do? You selectively oxidize and make a sulfone up here, and the rest is same. This is Julia-Kosiensky reactions. Kosiensky reaction. Kosiensky reaction means it's a little different. Okay. So what do? You require, that means you require a very selective oxidation, and what is the reagent? Ammonium molybdic acid. Ammonium molybdic acid. Ammonium molybdic acid. Okay. And this is quite often used in one of the labs in IIT. Which one is it? Somik's lab. Okay. And they often use the Julia-Kosiensky reaction. But for us, you have to, what you have to learn? It's very selective. What you see here, you have all kinds of sulfur, nitrogen, ring, all these things. You have a thiazole ring, it is not destroyed. You have two different kinds. You have two different kinds of nitrogen. There is a thiazole nitrogen and there is amide nitrogen. Amide nitrogen, as obvious, the lone pair is delocalized towards oxygen, if not available. Okay. But in this case, you have a nitrogen free, so lone pair free at the nitrogen of benzothiazole, that is not getting oxidized. You have two different kinds of sulfur. All of us know this. The sulfur of the ring is involved in the aromaticity of the system. So what is available then? What is, you have a free sulfur, you can selectively oxidize to the corresponding sulfone. Okay. Next item, of course, this is a very useful one. Many of you probably do not know. This is manganese dioxide. Manganese dioxide, how is it made? Manganese dioxide, how is it made? Manganese dioxide is made from manganese sulphate and potassium permanganate, and it can be used in three different conditions: neutral, basic, acidic. But most often in organic chemistry we use the neutral version, occasionally use in the acidic version, and the basic version is normally not used. It is not very strong, powerful oxidizing agent. So the most powerful oxidizing agent is manganese dioxide in acidic medium, followed by the neutral one. Okay. And but in heterocyclic chemistry, what you will see, it does not touch the heteroatoms. Unlike the hydrogen peroxide or the peroxide compounds, where you can form the N-oxide, sulfone, etc., etc. Like the example you will see here is an indole derivative, where nitrogen is protected as the sulfone, and then you have an aldehyde up here. If you try to do this oxidation with manganese dioxide, what you will see, it only specifically gives you this side chain oxidation, the rest remaining same, only the side chain is getting oxidized. Okay. So which is equivalent to sort of, you can say, the selenium diacid oxidations. Many times selenium diacid also does the same thing. That means this nitrogen is getting remaining unaffected, and the ring of the indole ring is not getting affected. Let us take about let us this one more pyrazolidine ring system, and you have a let us say carboxylic ester group up here. Now, if you try to do this this is an important area though, manganese dioxide, what do you expect? So, these are the example basically from there you can just draw this rather you can estimate the sense of oxidizing power of different oxidizing agents. Okay. In the first case there are what is that?
The ring which doesn't contain that carboxylate.
Tell me again.
The ring that doesn't contain that carboxylate acid.
Yes, would be oxidized. Yes. Okay. Let us say that's what no, I would assume first actually the alpha position. Alpha position nitrogen would oxidize to the corresponding ketone. That's what I would expect. Okay, because nitrogen can assist the formation of the carbocation alpha to it. So, one would expect a double bond up here oxygen and or on this side, but this is very good in heterocyclic cases especially for dehydrogenations. This is a replacement of DDQ, and one of the rings would be dehydrogenated. And in this case, which one? Guess. There are two rings, one without carboxylic acid, one ester, one is free. Actually, the one with carboxylic acid, because all of us know the most substituted double bonds are more stable. So, this is that classically you can do it. And one more example probably about this aromatization like thiazole. These thiazoles are very useful again in heterocyclic chemistry, and often these are made. And how do you aromatize? DDQ as expensive, toxic, all these things, but one can just nicely do it with manganese dioxide. Alternatively, or often this cupric bromide is used, or this is something probably you do not know, this bromo-trichloromethane and DBU. So, bromo-trichloromethane is a nice actually brominating agent. It brominates alpha positions, then dehydrogenation takes place, and eventually gets the aromatizations done. Okay. And then I have one more example, I think I will skip, but there are quite a few interesting example I will I think I will give you. This is I think many of you know, I guess, ruthenium tetroxide. Ruthenium tetroxide is a very useful one, very useful reagent. I mean, often we do not use it, but it's and one of the conditions is ruthenium trichloride, then sodium pyraiodate, and then triphasic system. Triphasic system means CCl4, then acetonitrile and water. This was published when we did my postdoc. I did my postdoc. Okay. So, this is due to again surplus. Throughout his life, he only did oxidation. Okay. And this is a very good method, very good reagent. Ruthenium trichloride, sodium pyrite is equivalent to ruthenium tetroxide, and it can do many oxidations. But just I will, in the context of heterocyclic chemistry, I will just tell you only one example, that is a furyl substituted compound. Then you have so many oxygen here and there, all these things. Then you have a side chain, this oxygen stereochemistry, everything. I mean, here and there different oxygens. I will not write the full structure. When you apply this reagent, what would you expect? These are all these actually benzyl group, that means benzoate, benzoyl group. So, benzoyl groups, all these oxygen. One of these oxygen is actually TBS. So, I mean it does not matter, that means all these oxygens are protected now. Yes. Okay. So, what do you expect? Again I taught this reagent in the last year, because it is one of the very useful and very unique oxidizing agent. Many times it does a lot of important things. Okay. Any idea, any answer from the class? No. Okay. So, that means furan here serves as the a carboxylic acid. If you recall, you have a different side chains on the benzene, and if the benzene is electron rich, that can be oxidized to the corresponding carboxylic acid, and side chains remaining other. That means this is reverse of potassium permanganate. If you take toluene, it gets oxidized to corresponding benzoic acid, but if you want to, let us say, from toluene to convert acetic acid, how do you do? Ruthenium tetroxide. Okay. And what else? Let me just these are all miscellaneous, let us say, kind of reaction. For example, you have now in heterocycle, you have a side chain oxidizing agent, and then IBX. Anybody knows what is the structure? Okay. Some of you know, I guess. It is a benzene ring and iodine, and then it is a carbonyl oxygen, and then what you will have a double bond up here and OH. Isobenzooxazole. I stands for iso, B stands for benzo, and X stands for oxazole. IBX is a now common, is a household name in organic chemistry. Who uses exclusively in our department? Again Somik routinely uses IBX. I think once upon a time he used to make it in grams and grams. Okay. What do you expect? It is a heteroatom. So, it does not undergo N oxidations, it does not undergo oxidative dearomatization. What it does, it gives a interesting thing here, oxygen this and then this one. That means it oxidizes the alcohol, and also it induces the deoxygenations. Okay. And we have very few minutes. I think I will go to the next. I mean, I am skipping this Davis oxidation. I think I will have one more important oxidation. This is, I think, this is the use of heterocycle in oxidation. It is not the oxidation of the heterocyclic system. It is the heterocyclic based oxidizing agent that is used in the literature. For example, if you are to require, if you are required to oxidize a primary alcohol to the corresponding carboxylic acid. Okay. So, how do you do it? Sodium chloride and tempo. Fine. I think you are very right. Actually, the name of the reaction I will write. If you do not want to remember, now is perfect, all right. And Lee oxidation. It was discovered in 1987, and this yes, you are. I mean, there are different kinds of the combinations. One can do phenyl iodinium acetate and tempo. This is one condition. The other could be sodium hypochlorite, that means bleaching powder, and tempo. So, I think the original one with the bleaching powder, the recent version is potassium phenyl iodinium diacetate. Okay. What is the beauty? I think I will just give you only one example that will tell you what is the beauty of this reagent. The structure of the molecule is like this. You have a benzene ring, dichloro, then dichloro, you have a benzyl, and then okay, and then you have amide here, and then you have a pyrrolidine structure, then you have it is a diol, 1,3-diol, and then you have nitrogen here. nitrogen, then CBZ protecting group, and here you have a carboxylic protecting group. So, likewise, I mean you have so many functionalities, right, and so many functionalities basically. Now, if you this annealy oxidation, in this case is a 4-methoxy sodium, the recipe is like this: sodium hypochlorite, then 4-methoxy tempo, that was the original one actually, 4-methoxy tempo, then potassium bromide catalytic and bicarbonate, sodium bicarbonate. What we will see, okay, it does not oxidize the benzylic CH2, it does not oxidize the benzene ring, it does not oxidize the nitrogen, it does not oxidize this nitrogen, this nitrogen is protected as CBZ, and you have a secondary OH group, it is not oxidized, only the last one is oxidized, I mean this remains free, this is, and then CBZ, and this one gets converted to the carboxylic acid. And I mean the oxidation of carboxylic acid is not that easy though. For example, if you have ethanol, you want to oxidize to carboxylic ester, what is the method? Not many methods. I mean classically we used to do all these oxidizing agents, potassium permanganate, potassium dichromate, all these things. Okay. So, but if you have little complex system, for example, at one point we tried to oxidize these two corresponding carboxylic acid. How do you do it? In our lab we do, right? How do you do it? You cannot do it, it is tough. Reason being, you have a double bond present now. So, that restricts your choice. But if you have this kind of reagent, some which are very selective towards the oxidation of the alcohol to the OH, and that you see here primary one. There are many methods, in the presence of primary you can oxidize the secondary, right. There are many methods. All the hypochlorite based oxidizing agents are actually selective towards the secondary alcohols, not the primary one, but what you see here in this case it is the primary one. Okay, that takes care of, I think I have skipped actually quite a few, but maybe if the time permits towards the end of this semester we will talk about it. Next time we will talk about what? Or you suggest something you want to know, you are eager to learn. Obvious. So nucleobases. So there are not much of chemistry there in nucleobases. Okay. Yes, that's only nucleophilicity, etc., etc. But